In 1900, Planck used energy quantization to explain the blackbody radiation. In the subsequent years, quantum theory had developed tremendously in the aspects of both fundamental understanding and applications. But the challenge for applying quantum mechanics remained, just as Dirac stated in 1929. The underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known, and the difficulty is only that the exact application of these laws leads to equations much too complicated to be solvable. It therefore becomes desirable that approximate practical methods of applying quantum mechanics should be developed, which can lead to an explanation of the main features of complex atomic systems without too much computation. We will demonstrate the complicated Schrödinger equation of a many-electron system of great interest, and the density functional theory as the approximate practical solution. A many-electron system is composed of positively charged nuclei and negatively charged electrons. Because the nuclei are moving much slower than the electrons, we can assume they are stationary and just focus on the motion of electrons, which is the so-called Born-Oppenheimer approximation. Therefore, we can write down the Schrödinger equation for many electrons in this way. The first term in the Hamiltonian is the kinetic energy of electrons. The second term describes the interaction between the positively charged nuclei and the negatively charged electrons. And the third term is coming from the interaction among electrons. The many electron wave function has to involve the coordinates of all electrons. In a system, the number of electrons can be on the order of magnitude of Avogadro's constant. As a result, we have to consider huge number of degrees of freedom when solving this many electron Schrödinger equation. Density functional theory is a great approximate practical method which allowed us to avoid solving the complicated many electron Schrödinger equation. In 1964, Holmberg and Cohen proved that the electron density of a system uniquely determines the system's ground state physical properties. So it would be great if we can find a system that gives the same electron density and at the same time is easier to solve. In 1965, Cohen and Sham proposed a single particle scheme to map the interacting system we are interested in to an artificial non-interacting system. The real interacting system and the fictional non-interacting system are connected by the same electron density. So instead of 3 position variables involved in the many electron wave function, we only need 3 position variables for the wave function in the single particle picture. Density functional theory transforms our task from solving the many electron Schrödinger equation to solving the one electron Kornsheimer equation. In the Kornsheimer equation, the first term is the electron's kinetic energy. The second term is the interaction between the electron and the nuclei, and the third term is describing the interaction among electrons in the sense of mean field approximation. Here we have one more term, the so-called exchange correlation potential, which incorporates the remaining electron-electron interactions. The electron density is obtained by summing up the squared wave function for all occupied energy states. In principle, density functional theory is exact for the ground state electron density and the total energy, but this exchange correlation term as the functional of electron density is unknown and must be approximated. There are 2 popular approximations for the exchange correlation functional. One is the local density approximation that depends solely on the value of the electron density at each point in space. This approximation was derived by considering the situation in a homogeneous electron gas, and therefore would be good for systems with slowly varying electron density. The other one is the PBE type generalized gradient approximation that takes into account the gradient of the electron density in addition to the density itself. The PBE approximation was first published in 1996 and had been cited more than 35,000 times by 2014. This paper was ranked 16 among 100 most highly cited papers of all time explored by Nature. With density functional theory, the number of variables we have to consider has been significantly reduced. For a crystal, the problem can be further simplified. Because a crystal is composed of unit cells, repeated over and over again along the lattice vectors A1, A2, and A3, there must exist some relationship between the unit cells. Bloch theorem reveals this relationship, that the electron wave function in a crystal can be written as a periodic function modulated by a plane wave. So in the wave function, the unknown part UNR is the same for different unit cells, which allows us to focus just on one unit cell instead of the whole crystal system. So basically, there are two steps we used to simplify our problem. First, density functional theory allowed us to use single particle scheme to study the original many electron system, but we still need to solve the Cauchy equation for wave functions in the whole space. Second, the translational invariance in a crystal structure leads to the Bloch theorem that allowed us to solve the Cauchy equation in a unit cell. There are several popular density functional theory software packages. Depending on the basis functions used in expanding the wave functions, they can be grouped into plane wave code, localized orbital code, and real space code. Among these packages, WASP is the most popular one and is commercial. It comes with a complete set of pseudopotentials for almost all the atoms, and is very convenient for performing simulations on various materials. Quantum Espresso is the most popular open source package and has functionalities similar to WASP. Siesta is very good for quantum transport study and is open source. In the future, I will use Quantum Espresso to demonstrate how to carry out practical density functional theory simulations